On a cold, clear morning in January of 1943, the SS Schenectady sat quietly at her dock in Portland, Oregon. She was a brand new Liberty ship, barely 10 weeks out of the Kaiser Shipyards, a vessel born of American industrial might and wartime urgency. The air was still, the harbor water like glass. No enemy aircraft threatened the sky, no submarine's torpedo lurked in the depths. The only sounds were the usual harbor noises, the cry of gulls, the distant clang of machinery, the gentle lapping of water against steel. Then, without the slightest warning, a sharp, percussive crack, like a giant's whip, echoed across the docks. It was a single, terrifying report that froze every man on the pier and aboard nearby vessels. In the moments that followed, a low, groaning rumble built into a shriek of tearing metal. Before the eyes of the horrified dockworkers and crew, the entire vessel fractured completely in two. Her hull split from her main deck down to her keel, as if sliced by an invisible, colossal blade. Sailors scrambled for safety as the bow and stern sections sagged away from each other, a grotesque V shape forming amidships. The ship's back was broken, not in a raging storm or in combat, but while she was tied safely to the pier. The Schenectady was not an isolated tragedy. That same bitter winter, another Liberty ship, the SS John P. Gaines simply broke apart in calm seas, succumbing to stresses that should have been routine. The SS Schenectady a T-2 tanker built using identical rushed methods, cracked so violently and severely that her crew abandoned ship in a panic, believing they had struck a mine. The epidemic was widespread and terrifying. Between 1943 and 1944, more than 2,500 Liberty ships reported serious structural failures, hairline cracks that became gaping holes, fractures snaking across decks, catastrophic splits that appeared without warning. At least 19 vessels broke completely in half. 3 more simply vanished at sea, disintegrating so rapidly and utterly that they could not even send a distress signal, their doom as silent as it was absolute. These were not war casualties sunk by enemy action. These were ships committing suicide, tearing themselves apart from the inside out. The United States had gambled its entire war strategy on the Liberty ship program. After the attack on Pearl Harbor threw the nation into a total two-ocean war, the need for cargo vessels was desperate, existential. The lifeline to Great Britain and the Soviet Union was being strangled by German U-boats, which were sinking Allied merchant ships faster than they could be replaced. Traditional shipbuilding was a craft of patience and skill, taking 8 months or more to produce a single freighter. The United States Maritime Commission could not wait that long. Into this breach stepped Henry J. Kaiser, a brash, visionary industrialist who had made his name building dams and highways, but who had never before built a ship. He promised something audacious, mass-produced freighters, constructed like automobiles rolling off a Detroit assembly line in weeks rather than months. His shipyards in Richmond, California, and elsewhere became crucibles of revolution. They employed radical new techniques, welding instead of time, consuming riveting, prefabricated sections built in separate shops, and then assembled like a monstrous puzzle, and assembly line logistics borrowed directly from the automotive industry. By late 1942, Kaiser's yards were performing miracles, launching Liberty ships in an astonishing average of 42 days. The propaganda machine celebrated this industrial prowess. Newsreels showed determined Rosie the Riveters, though they were now more often welders, transforming flat steel plates into seagoing vessels at impossible speeds. The SS Robert E. Peary became a national icon, a symbol of American ingenuity, constructed in a record-breaking 4 days, 15 hours and 29 minutes from keel, laying to launch. The nation cheered. The hemorrhaging of Allied shipping tonnage, devastated by U-boat wolf packs, finally seemed to be stanched by this endless flow of new hulls. Then the ships started to break. Not from torpedo damage or the fury of North Atlantic gales, but spontaneously, catastrophically, in conditions that should have been routine, while tied to a pier or sailing on a calm sea, naval architects and marine engineers were baffled. The welds, when inspected, looked solid and sound. The steel met all the standard specifications for shipbuilding. The designs themselves were based on proven, decades-old British blueprints. Yet, these Liberty ships were fracturing with the sudden, brittle violence of a porcelain teacup hit by a hammer. The cracks almost always started at points of sharp geometry. The corners of hatch openings, the bases of gun mounts, the square-off edges of the hull itself. Once a crack initiated, it would propagate through the continuously welded hull plates at terrifying speed, sometimes racing the entire length of a ship in a matter of seconds, unzipping the vessel faster than a man could run. The Maritime Commission convened emergency investigations. Panels of experts were assembled, committees formed. Metallurgists examined failed steel sections under microscopes, searching for impurities. Engineers pored over stress calculations, looking for errors. Naval inspectors crawled through fractured hulls with magnifying glasses and measuring instruments. Everyone was searching for a single, clear culprit. Bad steel, faulty welds, fundamental design flaws, inadequate quality control. But the evidence was contradictory, and while the committees debated and pointed fingers, the ships continued to split open. A deep-seated terror began to grow among the merchant marine sailors. They went to sea knowing the very hull beneath their feet might unzip without warning, spilling them into the killing cold of the Atlantic waters in minutes. The miracle of mass production had become a maritime nightmare, and nobody in a position of authority could explain why ships built in record time were failing in record numbers. The answer, when it finally came, emerged not from a panel of distinguished engineers or a university laboratory, but from the least likely source imaginable, a welder on the graveyard shift who, by the rigid hierarchies of the time, was not supposed to question the decisions of the engineering department. Her name was Bessie Hamill. She worked the night shift at Kaiser's Richmond Yard No. 3, one of the thousands of women who had flooded into the shipyards after the men shipped off to war. She had been welding hull sections for 8 months, long enough to develop a feel for the metal under her torch, an intuitive understanding of its behavior. And every night, she watched her team and others weld massive steel plates together in a sequence that, to her practiced eye, made no mechanical sense whatsoever. She saw welders starting at the edges of plates and working inward, or beginning at one end of a long, critical seam and running a continuous bead straight to the other end. As each of these welds cooled, the molten metal contracted, pulling and warping the plates with immense, invisible force. She could literally see the stress building, watch the steel distorting and buckling under the heat of her torch. When welders finished one section and moved immediately to an adjacent one, they were effectively locking that stress into the structure permanently. It was, she thought, like tightening the center bolts on a car wheel before securing the outer ones, a recipe for imbalance, strain, and ultimately failure. When she voiced her concerns to her foreman, she was dismissed. She was a welder, he told her, not an engineer. The welding sequences came from the engineering department, from men with college degrees and formal training in naval architecture. Their calculations were not to be questioned by a production line worker. But Hamill persisted. The evidence of her own eyes was too compelling to ignore. In November of 1943, mustering a courage that defied all protocol and could have easily cost her job, she requested a direct meeting with yard supervisors. She brought with her samples, test plates she had welded on her own time using different sequences. Some, welded in the traditional edge-to-center or end-to-end manner, showed significant warping and visible stress patterns. Others, welded from the center outward in a carefully planned, balanced sequence, lay flat and true with minimal distortion. The supervisors were initially skeptical. This was a woman, a production welder, challenging the established wisdom of their engineers. But one of them, more observant or perhaps less bound by convention than the others, was intrigued. He agreed to come down to the production line during Hamill's shift and simply watch, What he saw confirmed her observations in the most dramatic fashion. He saw welders, in their rush to meet production quotas, essentially torturing the steel, forcing it to accept stresses that it would carry for its entire service life. Every cooling weld was creating a zone of residual tension in the metal. The haphazard, unplanned construction sequence meant these internal stresses were not dissipating, but instead accumulating and concentrating at specific points, particularly at the sharp, unforgiving corners of hatch openings and other structural discontinuities. When those ships subsequently sailed into the cold of the North Atlantic, the steel itself became brittle. The locked-in residual stress from the shipyard, combined with this newfound embrittlement, created the perfect conditions for a catastrophic running fracture. Hemmel's insight was elegantly simple. Weld from the center of sections outward, allowing the thermal contraction stresses to dissipate toward the free edges, rather than being trapped and concentrated in the middle. Alternate welding locations around the structure to prevent heat and stress from building up in any single area. Never complete long, continuous welds in a single run. Instead, use a staggered, balanced sequence, a few inches here, a few feet away there, that distributed the cooling stresses evenly across the entire structure. These were not revolutionary new theories of metallurgy. They were practical, hands-on observations from someone who worked with the material every day, who felt the metal move and breathe and shrink under her torch, and who had correctly recognized the consequences of fighting against its natural behavior. By December of 1943, her observations had climbed the chain of command and reached the desk of Henry Kaiser himself. The industrialist now faced a brutal choice. The Liberty ship program was already under intense congressional and military scrutiny because of the cracking epidemic. Admitting that the fundamental problem was not the quality of the steel or the integrity of the individual welds, but the very sequence of construction, the process he had championed as a revolution, would mean acknowledging that every single ship built so far had systematic, potentially fatal flaws baked into their hulls from the moment of their birth. It would mean temporarily slowing down the breakneck production speeds, retraining thousands of welders, and redesigning the entire assembly process from the ground up. But it also meant potentially solving the fracture crisis that threatened to undermine America's entire maritime logistics chain and cost countless lives. Kaiser, to his immense credit, did not hesitate. He authorized immediate, full-scale testing of Hemmel's theories, pulling an entire hull section from the production line for experimental reconstruction. The metallurgists and engineers who had spent months analyzing failed ships were now, perhaps chagrined, taking instruction from a night shift welder who had never seen the inside of a college classroom. The test results were both damning and revelatory. When Kaiser's own technicians examined hull sections constructed using the conventional sequences versus those built with Hemmel's methods, the difference was measurable, dramatic, and undeniable. Residual stress gauges showed that traditional welds carried internal tensions exceeding 0 pounds per square inch, concentrated at key structural points. Hemmel's sequence sections, by contrast, distributed those stresses across much broader areas, with peak readings barely reaching 12.000 psi. The steel itself was identical. The welds were chemically and structurally indistinguishable. Only the order of operations had changed, yet the improvement in structural integrity was by a factor that the engineers initially refused to believe. The physics behind the mysterious failures finally came into sharp, clear focus. Steel is not a static, inert material. It is a dynamic, crystalline structure that responds powerfully to temperature changes. When a welder runs a torch along a seam, they are creating a localized temperature zone exceeding 500 degrees Fahrenheit. The metal in that zone expands dramatically. As it cools and solidifies, it contracts, but it is now fused to the surrounding, cold steel, which constrains that contraction. The result is a permanent state of residual tensile stress, a kind of frozen strain locked into the joint. Liberty ships were suffering from what metallurgists call brittle fracture propagation. The steel used in their hulls, a standard carbon steel designated as shipbuilding grade, performed adequately in the warm, temperate waters of a California shipyard. But it underwent a critical and deadly transformation in the near-freezing temperatures of the North Atlantic. Below roughly 40 degrees Fahrenheit, the steel's ductility, its ability to stretch and deform slightly without breaking, collapsed. Normally, a metal under stress will yield, bending rather than snapping. Cold steel loses that flexibility. It becomes brittle, more like glass or ceramic than the tough, forgiving material the welders had worked with in Richmond. When this brittle steel, already preloaded with immense residual stress from its construction, encountered a sharp corner, like the square edge of a cargo hatch, physics took over with brutal efficiency. A microscopic crack would initiate. In a ductile, stress-relieved steel, that tiny crack would quickly stop, its energy absorbed by the material's ability to yield and deform around its tip. But in brittle steel under high tension, the crack became a sprinting fracture. The massive energy stored in those residual stresses provided the fuel, and the crack would accelerate, sometimes exceeding the speed of sound in steel, racing through the hull like a zipper before bulkheads or frames could arrest it. The fracture of the SS Schenectady now made perfect, horrifying sense in hindsight. She had been built in the early winter, welded in sequences that maximized residual stress. Her hull carried tens of millions of pounds of locked-in tension. When the Portland morning dawned at 28 degrees, her steel became brittle. The immense stress concentration at the corner of a hatch initiated a crack. That crack found a straight, unimpeded path through the continuously welded deck plates. There were no riveted seams to slow it down, no natural stress relief points to stop it. The fracture consumed the ship in seconds, releasing decades worth of stored energy in one single catastrophic failure. This also illuminated why traditional riveted ships had never suffered from this problem on such a scale, and why welding, for all its speed and efficiency, seemed almost cursed. Riveted construction is inherently discontinuous. Each riveted plate is a separate element with a boundary. A crack that starts in one plate hits a riveted seam and stops. The overlapping plates and mechanical fasteners act as natural crack arresters. Welded ships, by contrast, are monolithic, continuous structures. A crack in one plate can run unimpeded through hundreds of feet of seamlessly joined steel. The very efficiency that made welded ships faster to build also made them uniquely vulnerable to a failure mode that riveted ships were structurally designed to avoid. The Liberty ship's square, doff angular design, specified by British architects for easier cargo handling, compounded the problem exponentially. Nobody had fully considered that sharp internal corners act as powerful stress concentrators, multiplying applied loads from waves and the ship's own motion by factors of 3 or 4. Every time a wave flexed the hull, it sent stress spikes hammering into those corners. Combined with the residual welding stress and the brittle cold steel, those corners became predestined crack initiation sites, little time bombs waiting for the right combination of cold and stress to trigger a catastrophic failure. Henry Kaiser now understood what the test results meant for his industrial empire and for the entire war effort. In January of 1944, he made a decision that would either vindicate his revolutionary methods or expose him as a reckless profiteer who had sent thousands of sailors to sea in death traps. He ordered a complete halt to Liberty ship production at his Richmond yards and diverted resources and brainpower to an entirely new class of vessel, the Victory ship. This was not a minor modification or a quick fix. It was a fundamental redesign built from the keel up around Bessie Hamel's welding observations and the hard-earned blood, soaked lessons written in fractured hulls across 2 oceans. The gamble was staggering. Liberty ships were still desperately needed. U-boats had sent over 200 Allied merchant vessels to the bottom since 1939. The planned invasion of Europe, still months away in early 1944, would require the largest amphibious logistics operation in human history. Every single cargo ship was critical. Yet Kaiser was betting that he could not only implement Hammel's sequenced welding system, but also redesign the hull to eliminate stress concentrations, improve the steel specifications, and somehow maintain production speeds that the world already considered miraculous. His competitors thought he had lost his mind. Congressional investigators sharpened their knives, ready to crucify him if production collapsed or the new designs failed. Kaiser's engineers now worked backward from the failure points. Every square corner in the Liberty design was replaced with generously rounded transitions. The hatch openings that had birthed so many fatal cracks were redesigned with large radii, eliminating the stress multipliers that turned normal loads into fracture initiators. The thicknesses of deck and hull plates were recalculated, not necessarily to add strength, but to ensure stress distribution matched the new, carefully planned welding sequences. Structural frames were repositioned to align with natural stress relief points, working in harmony with the welding pattern rather than fighting against it. The steel itself was changed. Kaiser's metallurgists specified a new alloy with dramatically improved load, temperature toughness. The carbon content was reduced slightly, and the manganese content was increased. Small, expensive additions of nickel, a rationed material usually reserved for armor plate, were justified by demonstrating that even a 0.25% nickel content dramatically improved the steel's resistance to brittle fracture. The Maritime Commission balked at the increased cost until Kaiser's team presented cold, hard calculations showing that preventing the loss of just one ship and its cargo would pay for the upgraded steel in 50 new vessels. By March of 1944, the new steel specification was approved. Then came the monumental task of retraining the entire workforce. The Richmond shipyards alone employed over 90 zero workers by early 1944. Thousands of them were welders who had learned their trade in week-long crash courses, mastering just enough technique to lay down straight, fast beads at production speed. Now they needed to understand the principles of sequencing, stress relief, and thermal management. Kaiser established intensive welding schools within the yards, pulling his most experienced and insightful welders, people like Bessie Hammel, off the production line to become instructors. Every welder was issued a detailed, numbered sequence card for each hull section. Weld number 1 here, number 2 there, number 3 in a completely different location. Precise choreography of fire and metal that could not be deviated from. The prefabrication system was expanded and refined dramatically. Rather than welding large sections together on the building ways, where sequencing was difficult to control under time pressure, Kaiser's planners broke the new Victory ships into smaller, more manageable modules constructed in dedicated, climate-controlled shops. A single bow section might comprise 50 separate prefabricated assemblies, each welded in optimal conditions using the perfect center-outward sequences and then stress, relieved in massive heating ovens before final assembly. This modular approach meant that welders could follow Hammel's method from the center of each small section without the physical constraints and pressures of assembling a full hull on the slipway. The skeptics had their ammunition when the first Victory ship keel was laid in February 1944. The construction of that first vessel took 18 days, still astonishing by pre-war standards but slower than the record. Breaking Liberty ship times, Kaiser's yards, the critics crowed, were no longer achieving miracles. They were building ships at merely impressive speeds. The second Victory ship took 16 days. The narrative of failure began to build. Critics declared the entire program a fiasco, proof that quality and speed were fundamentally incompatible. Kaiser ignored them. He was watching a different set of numbers entirely, the crack inspection reports. The first 2 Victory ships showed 0 stress cracks in post-construction inspection, not reduced cracks, but 0. By April of 1944, Richmond Yard No. 2 had been utterly transformed. It no longer resembled a chaotic, frantic traditional shipyard. It had become a precision choreography of steel, fire, and human coordination on a scale that would have seemed impossible just 2 years earlier. The yard now operated like an enormous, disciplined assembly plant, with distinct fabrication zones feeding a central assembly area where hulls took shape with a new kind of efficient speed. Kaiser had borrowed and improved upon Henry Ford's moving assembly line concept, but with a twist. Instead of the product moving, specialized teams rotated through stationary construction stations in perfectly timed intervals. The process began in the vast prefabrication sheds, massive covered structures where welders worked on hull sections no larger than 30 feet in any dimension. Each section came with its specific, color-coded sequence card. A bottom plate assembly might require 47 individual welds, each numbered and mapped. Welders started at position 1, always the geometric center of the section, and worked outward in a precise spiral or radial pattern. Supervisors patrolled the floor with checklists, ensuring no one skipped ahead or deviated from the plan. After every 10 welds, the entire section would be moved into a stress relief oven, heated to 100 degrees Fahrenheit, and then slowly cooled. This annealing process allowed the steel's crystalline structure to relax, dissipating the residual stresses before they could accumulate to dangerous levels. The steel itself now arrived pre-cut and formed from rolling mills that had retooled specifically for Victory ship production. Unlike the Liberty ships, where yard workers had to cut and shape plates on site, Victory ship components arrived ready for immediate assembly. Curved bow sections came pre-formed to exact specifications. Deck plates had pre-drilled bolt holes for temporary alignment. Frame sections were delivered as complete, pre-welded assemblies. This massive upfront preparation, done in controlled factory environments, eliminated variables and ensured a consistency that was impossible in the ad hoc atmosphere of the early Liberty yards. Final assembly on the building ways followed a radically different sequence. Instead of starting at the keel and building upward, Victory ships were assembled from large modules that came together almost simultaneously. The engine room section, the multiple cargo hold sections, the bow, and the stern, all were constructed in parallel in different parts of the yard, then lifted by colossal gantry cranes and positioned in a single, coordinated operation of breathtaking scale and precision. On May 12, 1944, Yard Number 2 executed its most ambitious assembly yet. 17 major modules, representing 85% of a complete hull, were positioned, aligned, and set in place in just 11 hours. Welders then connected these massive modules using the same center-outward sequences, but now they were joining already stress-relieved sections, rather than building stressed sections from scratch. The push toward a new, faster timeline became a reality through the relentless optimization of every single minute. Night shifts pre-positioned materials for the day shifts. Specialized teams did nothing but check alignment and weld quality, catching errors before they could propagate. Mobile cranes moved on scheduled routes, delivering components to welding stations within 5-minute windows. Welders worked in strict rotation, 30 minutes on the torch, 10 minutes of rest, maintaining consistent, high-quality work without the fatigue-induced errors that had plagued the marathon welding sessions of the Liberty program. Kaiser implemented what he called the critical path method, meticulously tracking which tasks were bottlenecks and which could proceed in parallel. If frame installation was ahead of schedule but pipe fitting was lagging, he shifted workers immediately, maintaining a perfect balance across all construction phases. Every delay, every deviation was documented and analyzed. Morning meetings reviewed the previous day's performance, identifying and solving problems before they could snowball into major delays. The new record came on June 27, 1944. The SS Benjamin Warner Victory ship hull number 23 was completed from keel, laying to sea trials in 5 days, 11 hours and 15 minutes. This was not a stripped-down demonstration hull. It was a fully equipped, combat-ready cargo vessel, complete with defensive armaments, a functioning electrical system, a live engine room, and every single weld executed to the new, rigorous stress relief protocols. Her hull carried no cracks. Her post-construction inspection revealed residual stress levels well within safe, normal operating ranges. When the *Warner* sailed out on her shakedown cruise, she performed flawlessly in sea conditions that would have fractured an early Liberty ship in half. The 5-day Victory ship was not just a stunt of speed. It represented a complete philosophical rethinking of how complex machines could be manufactured when sound engineering principles were perfectly aligned with practical construction reality. Bessie Hamel's simple observation on the graveyard shift had cascaded into a systematic transformation of industrial production. The Victory ships that emerged from Kaiser's redesigned production system were fundamentally different vessels from their Liberty predecessors. To a casual observer, they might have looked like similar cargo haulers with an identical mission, but the differences began at the molecular level of the steel and extended through every aspect of their design and construction. Where Liberty ships had been emergency stopgaps born of desperation, Victory ships were engineered solutions, their every detail addressing a failure mode written in the blood of sailors who had ridden fracturing hulls into the cold Atlantic. The improved steel specification proved its worth immediately. The new alloy, designated as killed steel because aluminum was added during production to remove oxygen, demonstrated dramatically improved toughness at low temperatures. Laboratory tests showed its transition temperature, the point where steel shifts from ductile to brittle behavior, had dropped from approximately 40 degrees Fahrenheit in Liberty ship steel to near 5 degrees Fahrenheit. This 35-degree improvement meant Victory ships retained their structural flexibility and shock absorbing capacity in conditions that would have turned a Liberty hull into a fragile, glass-like shell. The cost premium was about 8% per ton, but the performance gain was incalculable. Every structural detail reflected the new, hard-won understanding of stress concentration and crack propagation. The rounded hatch corners, which seemed like a minor aesthetic change, reduced local stress concentrations by over 60%. Engineering calculations showed that the sharp 90-degree corners in Liberty ships created stress multipliers of 5 to 4 times the nominal hull stress. The Victory ship's generous radii kept stress multipliers below 1.8. In practical terms, this meant a wave impact that would have initiated a catastrophic crack in a Liberty ship would merely cause a Victory ship's hull to flex safely within its normal elastic limits. The hull plates themselves were now installed with intentional crack arrestor features built directly into the structure. Rather than relying on continuous welds running for hundreds of feet, Victory ships incorporated strategically placed riveted seams. These hybrid connection points provided intentional discontinuities, places where a propagating crack would hit a mechanical joint, lose its energy and hopefully stop before it could consume the entire vessel. The design philosophy had shifted. It now accepted that cracks might still initiate, but it engineered multiple redundant arrest mechanisms to prevent catastrophic propagation. It was a form of defensive engineering, planning for failure modes rather than assuming perfection could be achieved. Structural frames were doubled and reinforced at critical stress points, creating redundant load paths. If one frame were to develop a crack, the adjacent frames could carry the load long enough for the ship to make port and undergo repairs. Liberty ships had possessed no such redundancy. A single frame failure often led to a progressive, cascading collapse as loads redistributed to already overstressed adjacent structures. A Victory ship could sustain battle damage or structural failure that would have sent a Liberty ship to the bottom and still remain operational, able to limp to port on a compromised but functional skeleton. The welding sequences developed from Bessie Hamel's observations were now codified into exhaustive, detailed procedures that governed every joint in the ship. The procedure manuals ran to hundreds of pages, specifying not just the sequence but the thermal management between welds. Welders learned to monitor the interpass temperature, the heat level of the base metal between successive weld passes. If the steel exceeded 400 degrees Fahrenheit, work stopped until it cooled naturally. This prevented the cumulative heat buildup that had caused massive distortion and warping in Liberty ship construction, where welders often worked continuously on long seams, superheating the steel into permanently stressed and deformed configurations. Quality control became obsessive, uncompromising. Every completed weld received magnetic particle inspection, a technique where iron powder and a magnetic field revealed microscopic cracks invisible to the naked eye. Ultrasonic testing checked the internal quality of the welds, ensuring full penetration and the absence of hidden voids or slag inclusions. For the most critical structural welds, X-ray inspection was used, producing permanent photographic records of their integrity. Ships were not launched until teams of inspectors had certified that every single weld met the new, stringent specifications. The rejection rate was high initially. Nearly 15% of welds failed inspection on the first few Victory ships. But the welders, supported by better training and clearer procedures, learned quickly. By mid-1944, rejection rates had plummeted to below 3%. A powerful testament to the effectiveness of the new system. The ultimate proof, however, emerged not in the shipyard, but in the brutal theatre of operational service. Between June 1944 and the war's end in August 1945, 531 Victory ships entered service with the Allied Merchant Marine. Not a single one suffered a catastrophic hull failure. A handful of vessels developed minor cracks, small stress concentrations that vigilant inspections caught long before they could propagate. These cracks were repaired using the same stress, relief welding procedures, and the ships returned to duty without further incident. The contrast with the Liberty ships was absolute, and it was damning. The human arithmetic of Victory ships versus Liberty ships played out across the Atlantic and Pacific in 1944 and 1945, written in lives saved and missions completed that would have ended in disaster with the earlier vessels. The SS Wanda Fuka*, a Victory ship, hit a mine off Okinawa in April 1945. The explosion tore a 20-foot gash in her hull below the waterline. The crew, steeped in the grim lore of the Liberty ships, expected the dreaded catastrophic crack propagation to begin at any moment, dooming the ship. Instead, the fracture ran a short distance and then stopped dead at the first riveted crack or seam. The Wanda Fuka* retained her structural integrity, made port under her own power, was repaired in 6 days and returned to service. A Liberty ship, the SS Richard Hovey*, suffering a comparable mine strike in February 1945, cracked longitudinally for over 90 feet, broke her keel, and sank in 14 minutes with the loss of 37 crew members. The success of the entire Pacific campaign's island-hopping strategy would have been far more precarious without the reliability of the Victory ships. By June 1944, American forces were pushing across the vast expanse of the Central Pacific toward the Philippines and ultimately Japan. Each island conquest required millions of tons of supplies, ammunition, fuel, food, equipment to be moved across thousands of miles of open ocean. Liberty ships could make the voyage, but their structural fragility often meant reduced cargo loads in rough seas, slower transit speeds to minimize hull stress, and the constant gnawing fear of a catastrophic failure far from any hope of rescue. Victory ships, by contrast, could run at full loads and their designed speed of 15 knots, 3 knots faster than Liberty ships, through typhoon-prone waters, their crews free from the paralyzing fear that a cold night and a rough sea would suddenly split the hull in two. The numbers told the story with cold, hard logic. Between D-Day in June 1944 and V.J. Day in August 1945, Victory ships moved over 18 million tons of cargo for the Allied war effort without a single loss to structural failure. They operated in the murderous North Atlantic convoy routes where water temperatures routinely dropped below 35 degrees Fahrenheit, conditions that had fractured dozens of Liberty ships. They sailed the treacherous Arctic routes to Murmansk carrying lead, lease supplies to the Soviet Union, where seawater temperatures near freezing had made service on a Liberty ship a terrifying gamble. The SS Hobart Baker a Victory ship, made 17 grueling Murmansk runs without developing a single stress crack. The Liberty ship John Walker running the same brutal route, developed major cracks on only her second voyage and was permanently withdrawn from Arctic service. Crew morale underwent a profound transformation when sailors transferred from Liberty ships to the new Victory vessels. Oral histories collected after the war vividly reveal the psychological burden of serving aboard ships known to break apart spontaneously. Merchant mariners spoke of constant low-grade anxiety, especially when sailing in cold weather. Sleep was difficult, as every groan and creak of the working hull might be the harbinger of an imminent fatal fracture. Some sailors actively requested transfers, or simply refused to ship out on certain Liberty vessels with known cracking histories. The Victory ships restored that lost confidence. Crews pushed these new vessels hard because they knew the ships could take the punishment. That confidence translated directly into mission effectiveness, faster turnarounds in port, a willingness to sail in marginal weather, and more aggressive maneuvering when under air attack, all of which saved lives and won battles. The Battle of Leyte Gulf in October 1944 provided a dramatic demonstration of the Victory ship's combat resilience under conditions that would have devastated a Liberty ship fleet. 16 Victory ships supported the massive invasion fleet, hauling critical ammunition, aviation fuel, and general supplies through relentless kamikaze attacks and typhoon-strength weather. The SS Kyle Johnson took a near miss from a bomb that buckled her deck plates and cracked 3 mainframe sections. Yet, thanks to her structural redundancy and crack arrestor features, the damage was contained. She continued her vital unloading operations under fire for 4 full days before finally withdrawing for permanent repairs. A Liberty ship with similar damage would almost certainly have suffered progressive cracking, forcing the crew to abandon ship as the fractures raced beyond any hope of control. The final economic calculation was brutal, but unequivocally clear. Each Liberty ship had cost approximately $2 million to build. The Victory ships cost $6 million each, 30% more expensive. But a Liberty ship, based on the actual failure rates through 1944, had a 4.6% chance of suffering a catastrophic structural failure during her service life. Those failures killed an average of 18 crew members per incident, and destroyed cargo worth 3 to 5 times the ship's own construction cost. The Victory ship's zero failure rate meant the additional $600,000 construction cost was recovered within the first 6 months of service simply through eliminated losses and dramatically reduced war risk insurance premiums. By the war's end, merchant mariners had coined a grim saying that perfectly captured the difference. Liberty ships were built by the mile and cut off by the yard. Victory ships were built by the inch and measured by the year. Those inches, the meticulous attention to welding sequence, the obsessive quality control, the thoughtfully engineered crack arresters, meant decades of reliable service life instead of desperate prayers every time the hull groaned in a cold sea. Bessie Hamill returned to civilian life in 1946 without fanfare or public recognition. She received no medals, never testified before a congressional committee, and never saw her name in the technical papers and engineering journals that later documented the welding revolution she had sparked. The established engineering and naval architecture communities absorbed her insights, repackaged them in sophisticated mathematical language and academic terminology, and published them as if these discoveries had emerged from formal laboratory research, rather than from a night shift welder. Practical, hands-on observation. For decades, welding textbooks taught the principles of stress, relief, sequencing without ever mentioning the woman who had first recognized its critical necessity while watching hull plates warp under the glare of her torch. Yet, her legacy permeates modern engineering in ways that reach far beyond shipbuilding. Every major welded structure built today, from the soaring steel frames of skyscrapers to the vast networks of cross-country pipelines to the massive pressure vessels in chemical plants, follows sequencing protocols and quality control standards descended directly from the procedures developed at the Richmond Shipyard in 1944. The American Welding Society's Structural Welding Code, first published in 1947, codified center-outward welding sequences and stress relief requirements as mandatory standards for the entire industry. The construction of the 800-mile Trans-Alaska Pipeline in the 1970s, for instance, relied explicitly on welding procedures that referenced Victory ship methods to prevent cold weather cracking in the brutal Arctic environment. That pipeline, a ribbon of welded steel carrying hot oil through sub-zero temperatures, exists in no small part because engineers had finally internalized the lessons that Bessie Hamill had first brought to light. Modern bridge construction inherited these same life-saving principles. The catastrophic failure of the Silver Bridge at Point Pleasant, West Virginia, in December 1967, which killed 46 people, was found to have been caused in part by a tiny crack that grew from a point of high residual stress in a welded eye-bar joint. The subsequent investigation and the major code revisions that followed mandated the same kinds of sequencing and inspection protocols that the Victory ship program had proven essential 2 decades earlier. Every welded highway and railway bridge built since incorporates those requirements. The seismic retrofitting of the Golden Gate Bridge in the 1990s, which added thousands of tons of welded steel reinforcement, used computer-modeled welding sequences optimized by powerful software to minimize residual stress, a high-tech, sophisticated version of exactly what Hamill had demonstrated with her hand-welded test plates back in 1943. The offshore oil industry learned this lesson repeatedly, always at a terrible cost. The Alexander L. Kielland platform disaster in the North Sea in 1980, which capsized and killed 123 oil workers, was traced partially to fatigue cracks that propagated from a small, improperly welded attachment point, where residual stresses had concentrated. The Piper Alpha platform explosion in 1988, which killed 167 men, began with a crack in a welded pipe connection that had accumulated dangerous levels of residual stress. Each of these tragedies prompted exhaustive investigations, and each investigation rediscovered the fundamental principles that Victory ship construction had proven on a massive scale 40 years earlier. Modern offshore construction standards now universally require stress relief heat treatment for all critical welds, a direct and poignant echo of the massive ovens Kaiser had installed in Richmond's prefabrication shops. Perhaps the most demanding application of these principles is in the construction of nuclear reactor pressure vessels. These colossal steel shells, which must contain the immense pressures and temperatures of a nuclear reaction for decades without fail, cannot tolerate even the most microscopic crack initiation point. The welding sequences for these vessels are planned with computational precision, using finite element analysis to simulate thermal effects and predict residual stresses before the first weld is ever struck. The entire completed vessel is then subjected to a prolonged post-weld heat treatment in an enormous oven, a process that exactly mirrors on a more precise scale the stress relieving of Victory ship modules. The engineers who first designed these procedures in the 1950s and 60s explicitly studied the Victory ship construction records and failure analyses as their foundational reference. Bessie Hamill's observation did more than just fix a problem in shipbuilding, it fundamentally altered the very philosophy of engineering. Before the Victory ships, design and construction were often separate, siloed domains. Engineers created the designs and specified the materials. Fabricators executed the plans, and rarely did the two groups deeply communicate about how the construction methods themselves could fundamentally affect the structural performance of the final product. The Liberty ship crisis and its resolution proved, in the most dramatic way possible, that fabrication sequence was not a mere detail of production. It was as critical a design parameter as material selection or structural geometry. Modern engineering education now universally includes manufacturing processes, as an integral component of design courses. Students learn that a theoretically perfect design, if executed with a poor fabrication sequence, can produce an inferior and even dangerous result, while a modest design built with proper, thoughtful procedures can achieve unparalleled reliability. The 5-day construction timeline for the Victory ships, while a stunning achievement of logistics, was never the true miracle. Kaiser's yards could have maintained the 4-day Liberty ship pace indefinitely, churning out defective vessels that looked perfectly seaworthy until the moment they fractured in cold water. The real miracle was having the courage to slow down, to pause, to listen, and to redesign. It was the willingness to halt a successful production line based on the insight of a frontline worker, to admit that established engineering theory had missed something crucial that practical observation had caught. It was the decision to redesign an entire system around observed physical reality rather than defending flawed assumptions. That was the profound revolution. Every modern manufacturing and quality management methodology, from Six Sigma to lean production to total quality management, embeds this core principle at its heart, that the worker who performs the task every day, who observes the process in action, often sees truths and understands nuances that the engineer calculating from a distant office cannot. The person on the front line is not just a pair of hands, they are a source of invaluable ground-level intelligence. Bessie Hamill died in relative obscurity in Sacramento in 1987. Her obituary in the local paper was brief, mentioning only that she had worked in the wartime shipyards. There were no national headlines, no posthumous awards, but her legacy is everywhere. It is in the welded steel of every skyscraper that defines our city skylines, in every pipeline that carries energy across continents, in every bridge that spans a river, in every pressure vessel that contains awesome forces, and in every nuclear reactor that provides power safely. All of these structures carry within them, in their sequenced welds and their stress-relieved joints, the silent, unacknowledged testimony of the welder on the graveyard shift who looked at a warping steel plate and asked why, and who refused to accept "that's how it's always done" as a sufficient answer. Her story is a permanent part of the skeleton of our modern world, a hidden pillar of safety and reliability forged in the fire of wartime necessity and a woman's unwavering conviction.